Hello students, welcome to HSC Chemistry, the acidic environment, and today I want to have a look at some titration calculations. Now this is going to be part of your assessment task, and so therefore it's very important that you can follow the procedures not only to carry out the titration, but that once you've got a set of values you know what you're going to do with them. So that's what this video is all about. Titration questions always come up in HSCs. They're one of the common denominators amongst all of the past HSC papers. There's always a question on titration somewhere. Sometimes it's a 1-mark question, you've still got to do a lot of steps and calculations. Sometimes they're multiple mark questions with lots of steps, and sometimes they're just about procedures, how you can you analyze examples of good method and carrying them out. But on this video we want to concentrate on the actual calculations themselves. So allowing for the fact that you're going to have good techniques, repeat your titrations so you've got some consistent results and all of that sort of stuff. One of the most important things that we can look at is the mole ratio, because the mole ratio is not always going to be 1-to-1. A monoprotic acid will release 1 H+ ion per molecule, diprotic will release 2, and triprotic obviously will release 3 H+ ions per molecule. So therefore we would have a ratio of 1-to-3 acid to base if we were to titrate a triprotic acid against, for example, sodium hydroxide. So this is one of the reasons why the mole ratio is very important, and it's easy to make a mistake at this point, so you need to make sure that you're very consistent with your setting out. And today we're going to look at a way of setting things out which you may or may not choose to use. So once we've worked out whether our acid is monoprotic, diprotic or triprotic, we then work out how many moles of acid are needed in order to neutralize the base. So that's when we may be looking at a 1-to-1 ratio, maybe a 1-to-2 ratio, maybe a 2-to-1 ratio, or 1-to-3, and so on. The mole ratio is very important because it's going to be a critical step in making sure that we get to the correct answer. Once we've got our mole ratio, we then need to look at how we're going to calculate our number of moles. Is the number of moles going to come from a solid, in which case we will have mass, and we'll need to know molar mass. So there may be acids that we should already know the formula for, and therefore we can calculate the molar mass, and then we'll just do number of moles is equal to mass over molar mass. Or is it going to be a liquid? And if it's a liquid, then we're looking for concentration. Relationship between concentration is number of moles and volume. So concentration is the number of moles divided by the volume. So it depends whether we're looking at a solid or a liquid as to how we're going to calculate our values for the number of moles. So let's have a look at an example to kick us off then. So we know that sodium hydroxide is a very good solution to use in titration because it's a strong base, but it is not a primary standard, okay? Not a primary. Okay, there's another video which outlines the characteristics of a primary standard, and unfortunately sodium hydroxide does not fit into that category. So if we want to use it, we must standardize it first. We must find its concentration, find the concentration of that. How do we do that? The easiest way to do that is with an organic acid. So you might titrate against oxalic or tartaric or citric or whatever. Okay. Depending on what you use will affect these particular mole ratios. So let's say, for example, we look at something like tartaric acid, which is C4H6O6, and it's diprotic acid. So to just put some numbers together, for example, it may well be that we have to first of all start off with a mass. So we might have to weigh our tartaric acid first. So if we were, for example, to weigh out 1.5 grams, so you would do this on a electronic balance, and depending on how accurate your balance is, you may be able to get it to 1 decimal place, 2 decimal places, maybe even 3 decimal places. Okay, the more decimal places you can get it to, the more accurate it will be. So let's say, for the argument's sake, our mass of organic acid was 1.5 grams. Now we need to calculate the molar mass, so we do the calculation of the molar mass based on the molecular formula. So carbon is 4 times 12, and then hydrogen is 6 times 1. Let me just round things a little bit for you. Of course, you won't do this if you're going to be doing this as an actual exercise. So 48 and 6 and 3296. So that's 102, 150. Okay. So just to round it off at 150. So the molar mass is 150 grams. So now I'm going to go up. Okay. I can get to the number of moles by dividing the mass by the molar mass. Okay. Number of moles. Let me just pop this over here. Number of moles is equal to mass on molar mass. So therefore I have to grab my calculator, which I'll quickly do over here, and you can probably do that one in your head if you're good at moving decimal places. If you're not, do your calculator. I know it can get stressful in exams, but when we do that, we find that the value here is 0.01, okay, moles. This is where we now move across. So our ratio is 1 to 2, and therefore we must double the number of moles of base. So if 0.01 moles of acid are reacting, then we need 0.02 moles of the base in order for that to have a neutralization. Okay? So then, now we've got across, now we need to go down in order to get to our concentration. But in order to calculate the concentration, we need one more value. We need our volume. The volume comes from the titration. So this is going to be our average titer. So the average value of all the titrations you run. So usually this is going to involve at least 3 values, and you will remove outliers. You don't want any values there that have been part of your bucket run or are within probably more than about 0.2 of a mil of each other. And because we're just putting some numbers together at the moment, let's say that you had carried this out and it took 30 mils. So 30.0 mils was your average titration. So in order to find the concentration, we need number of moles over volume, but our concentration is always going to be in moles per litre, so we need to convert this to litres. So it's going to be 0.03 litres. So we have 0.02 divided by 0.03, and that's going to be 0.676666 moles per litre. So I'm going to keep that value, 0.67 moles per litre, for the value of the base. Because once we've standardized our base, so now we know that what the concentration of the sodium hydroxide solution is, now we can find an unknown. Now we can do something like checking out how much acetic acid is in vinegar. Okay? So what we're going to do is we're going to, again, carry out a titration. Now, if we are titrating against the base, and if we're using something like phenolphthalein, then we'll have to have that in the burette, because if it's not in the burette, then we're going from a pink solution to a colorless solution, and that's much more difficult. So if we use phenolphthalein, then the base is going, so this is going to again come from the average titer. And if we're going to do this, then we're going to have to work out how much we're going to need from here. So let's say we decide to titrate against a 10 ml aliquot. Okay, so this is going to be measured with our pipette. Hopefully a bulb pipette or something like that. It's going to give us an aliquot of 10 mils of vinegar. So this time, once again, we're going to go up. And in this case, if the acid is vinegar, which is acetic acid or ethanoic acid, CH2, CH3, COOH, then this is monoprotic. And then if this is sodium hydroxide, then that is also only liberating one OH minus, so the ratio here will be 1 to 1, which is good. So what we're going to need to do is to carry out our titration. If we've carried out our titration, we've got our average, and let's just say again, to make up some numbers, that this particular one takes an average of 4.3 mils. So it's a very short titration, very quick one. Again, we've got to convert that 0.0043 litres. And then if we go up, our number of moles is equal to CV. So that's going to be equal to 4.3 times 10 to the minus 3 times 0.67. And so that is going to be, let me just do that on the calculator. So it's basically 2.87 times 10 to the minus 3 moles. Now, this time we're going the opposite direction. So now we use the mole ratio 1 to 1. Okay, that makes life nice and easy because it means we can now just put the same number here, 2.87 times 10 to the minus 3. And then, once we're here, we go down. 2.87 times 10 to the minus 3. 10 mils is the same as 0.01 litres. So we're going to divide 2.87 times 10 to the minus 3 by 0.01, so concentration is in number of moles on volume, and therefore the concentration is going to be 0.287 molar. So here's a question from the 2009 paper. It's question 14, and once again, you'll probably figured out that this is a multiple choice question, but what I've done is again turned it into a question so we can solve it. And this is one of the problems with some of these titration questions, because they do sometimes come up as multiple choice questions, and it's a lot of calculation work for just the 1 mark. So if you're setting this out in an exam, you may want to sort of come back to a question like this where you know there's a lot of work involved for just 1 mark. But I'm not going to give you the options. We're going to try and see if we can solve this one. So here's the question. Maybe pause the video here and have a go. So how'd you do? I've taken all of these numbers. Okay, so the critical ones are the aliquot, how much of the lemon juice we have, our concentration of sodium hydroxide, and our average titer. Now we've also got this value over here for citric acid of 192.12 grams, and we also want to remember that citric acid is triprotic. So let's see if we can keep all of these things in mind and move on to the final slide. I'm going to put down here 192.12 grams for the molar mass of the citric acid. So here, this is citric acid. We know citric acid is triprotic, and because we're titrating against sodium hydroxide, the mole ratio is going to be 1 to 3 this time. This is our average titer. This is the concentration of the sodium hydroxide, and this was our aliquot from our pipette. So now we go up. So we multiply 0.55 times 0.0295, and that gives us a value of 0.016. Keep these numbers in your calculator. as you're doing these calculations, but write them down so that your teacher can follow your steps if you get something wrong. Okay, if you get the right answers, we kind of assume you're doing the right thing most of the time. But if you're getting wrong answers, then we need to know where you're making those mistakes so we can point them out to you. So once you've got this, then we use our mole ratio as we move across. So 3 to 1 means we're going to have to divide by 3 to get this value over here. So I'm going to just divide this by 3. And if, for example, you just used a 1-to-1 ratio instead of dividing by 3, then that's where you could make a mistake. So over here, I've got 5.41 times 10 to the minus 3. And then I'm going to go down. So when I go down, I get my number, and I'm going to divide that by 0.025, and it gives me a value of 0.216 moles per litre. Now, the only problem with this question, it's not quite finished because the answer actually gave you a value in grams per litre. So therefore, if we want grams per litre, then what we're going to have to do is multiply our number by 192. So if we multiply that by its molecular mass, 192.12, then I am going to get a value of, so it's that times that, which gives me a number equal to 41.6 grams per litre. Thanks for watching.